Hi, we are group number 8 and we are going to present our project design and simulation of a centrifugal pump. Index, introduction, literature review, materials and methods, results and discussions, and finally conclusions. Objective 1. Design and simulate a pump according to the data obtained by the Rumpus pump operation curves. 2. Using Excel Autodesk Inventor 2022 and Star CCM Plus, create a good design for a centrifugal pump that allows the interpretation and identification of the physical models involved. 3. Analyze through operating curves the behavior and performance of a pump at the different volumetric flows. What is a pump? A centrifugal pump is a machine capable of transforming mechanical energy into kinetic energy. This kind of pump are the most used in the industry. The industries that use these pumps the most are a chemical industry, the cosmetic industry, and the food industry. Common problems with the simulation of this pump. What we want to achieve is to face and to minimize some common problems in centrifugal pumps, like a cavitation, lack of suction, incorrect flow, the impeller slips of its axis of rotation, and no alignment in its part.
Now, here are some important concepts that should keep in mind for design purposes. So, in the state of the art, we can highlight the Navier-Stokes equation of state that allows describing the behavior of fluids. And this is important because it allows them to be applied to CFD simulation and modeling purposes. We also have cavitation, and it causes damage to the pump, the impeller, such as erosion. And also, it's important to mention the viscous flow pumping, highlighting that when the viscosity increases, the performance of the pump changes and it decreases. Well, here are the most important numerical calculations for the design of the pump. For example, the outlet diameter of the impeller, which we will see later, represented in its geometry, as well as the number of blades. Here are the velocity triangles. We can see highlighted certain values that we will see expressed later, as is the profile speed and these last three values that can be seen in the plans obtained, which is in accordance with what is expressed here.
We chose a thin measure and a prism layer measure so that we can transmit properly the information near the surface with a base size of 1 centimeter that is exactly the same as the target surface size. Minimum surface size is 10% as it is equal of the prism layer total thickness. We chose 5 prismatic layers which could adapt properly to the edges. 3 optimization cycles with a quality threshold of 0.6, 2 controls for no prismatic layers at the inlet, the outlet, and the interfaces so that the information could be transmitted properly, and for the volute the cells were configured at 200% of base size.
The Excel values were used in Inventor to make these geometries with the program tools such as extrusion. For the impeller, we see the mentioned diameter of 270, and we can also see that it's a closed impeller and the 7 blades. In the case of volute, it was verified that the impeller fit well and that it was centered correctly. The last one is the assembly, and here we can see the cycle in the correct range and the inlet and the outlet of 10 centimeters and 8 centimeters respectively.
Data against the CFD obtained data for water and for oil. We can see that the behavior of all of these graphics, the brake power, the efficiency, and the total head against the flow rate, it's really similar between them. So we can see that it doesn't matter the properties of the fluid, they are always going to be conducted by the pump design, and it's going to accomplish the principal objective, that is to simulate properly the behavior of the fluid inside of the pump.
The rotational velocity was constant and the same value was used for both simulations, oil and water, which led to velocity magnitude in the rotation zone always being the same range of values. We can also observe how it is fulfilled that U2 is the outlet velocity of the impeller. In the specific case of water, here we observe how the values of the wall-way plus are not within to the expected range, which is from 0 to 5, and this may be due to the fact that when the flow is greater, the shear rate increases, and therefore the behavior of the fluid when it is close to the walls moves away from the model. To avoid this, it's recommended to do simulation with a thinner mesh. To find out if is there cavitation or not in our pump, we take the value of 2338 pascals for the steam pressure, where regions in very dark blue there is no cavitation, but rather they are areas of negative pressure. The phenomenon of cavitation is observed in light areas. As is evidenced in some cases, this is more common at inner tip of the blades like this, so it is recommended to vary the angle of attack to prevent this from happening.
Translate that it will give us less shear stress. The shear stress is directly proportional to the U plus, and the U plus is exactly the same as the Y plus in a range of 1 to 5 Y plus, and as we can see in the graph in the scenes result, this matches exactly with the behavior of the all Y plus into the pump. We were not able to find a vapor pressure value for the oil at 20 degrees Celsius, but we found one for a medium molecular oil vapor pressure at 50 degrees Celsius, which is 0.07 pascals, and we know that the less temperature is going to be the less vapor pressure, so we decided to use this as the reference vapor pressure for the oil, and as we can see it is really low. This is why we don't expect to have any cavitation on the pump. We can see that we have points with blue dots, but this just means that the total pressure in that point is negative, and it's not, that does not mean that it's going to have cavitation. Finally, the conclusions. First of all, for us, it is viable to add an extra blade to the impeller's design, because this will increase the angle of attack, and this will help to reduce the chances of having cavitation in the impeller. The second conclusion that we have is that the Grundfos pump reference was properly simulated because of the pump operation curves that we obtained and the similarity of the behavior that it has to the original Grundfos pump curves. And finally, we would like to recommend for the next study of this CFD centrifugal pump simulation to implement the study with another fluid that has a bigger, a greater density and that is more viscous than water, so that it can be certified that the behavior of the pump we designed is aligned to the original one. Thank you very much, and now the references. Remember, this was group 8. Thank you very much for your attention.